deep reinforcement learning. And maybe some of you will wonder what the entrepreneur in residence is, and he will definitely explain. And without further ado, please welcome Mr. Devlin.
In the back, can you guys hear me all right? Is this sort of, okay. All right, so this is the first slide, School of Business Center for Innovation and Ethics. This is who we report to as an entrepreneur in residence. It's myself and Brad Downs over here in the front. Under Professor Michaels, our job is, our mandate, if you will, is to promote entrepreneurship, innovation on campus. Our intent is to solve big ideas for any means sort of necessary, whether that's technology motivated. So if any of you have any entrepreneurial initiatives, I mean, as an engineer or an innovator, you very well may have now or in the future, stop by and contact us, and we'll talk to you about our experience as entrepreneurs starting a company and the progress that we took over 10 years to eventual acquisition, and now we're here. So stop by and say hello. Okay, today we're going to talk about deep reinforcement learning. Out of curiosity, does anybody here have a pet at home, preferably a dog? Anybody help train that dog in any way? Okay, enough. If you don't have a pet or a dog, it's fine. We're going to not think of this as from the perspective of being a trainer, but from the perspective of being this cute little adorable puppy that was just adopted by a nice couple and brought home. And you think you're this puppy and you show up in this new environment, and you don't know anything about this environment. What do? You just sort of start exploring, trying to learn new things. So maybe you go up to your new owner and you kind of sit there and your owner pets you. And you go, that's cool. You get this reward for just kind of sitting next to your owner in a cute fashion. Maybe the next day you go into your owner's closet and there's these things that are very chewable and they turn out to be your owner's shoes and you chew on them and you get scolded. So let's just call that a negative reward. And you don't necessarily know at this point that chewing on shoes is a bad thing per se. You just know that you got scolded for doing it. So the next day you go back in that closet, you chew again, one of these shoes, and you get scolded again. Again, sort of this negative reward. And then there's this whole thing of like, going to the bathroom. Sometimes you go inside, sometimes you go outside. Ultimately, you have to go. And sometimes you get rewarded with, I don't know, a treat. Other times you get scolded and yelled at and told no. Again, sort of this negative reward. But over time, what ends up happening is, as this puppy, you grow to be housebroken. And you learn to do things like sitting and whatever. And it's all sort of through this exploration of this environment. And it turns out that this type of learning is how many of us learn in a day-to-day. They're getting feedback from our environment. And that's the basis and the fundamental of this idea of reinforcement learning. Reinforcement learning is a very, very, very hyped area of research in the AI community. And the reason is because it's sort of like what many believe is the foundation to artificial general intelligence, or this idea that like AI will outperform humans across various tasks. Like you've seen this in like utopian or dystopian movies with machines, like depending on which side of the argument you're on. So let's talk about gameplay. All right. So for a long time, researchers in the deep learning community, or the reinforcement learning community, have used games as sort of a barometer or metric to sort of determine how good their AI is. And at one point in time, it was almost assumed that if we could create an AI using this reinforcement learning technique, that we would have achieved artificial intelligence. And it turns out that wasn't that big of a deal. Things went cold for a while. Then in 2013, this company called DeepMind created an AI to play multiple games of Atari at human level performance. We'll talk about that in a bit, but this paper that they released ended up being worth about $500 million because Google bought them. And the good news about this talk is we're actually going to learn the algorithm how they did that today. So maybe there's wealth in the future and greatness and glory in your futures. After Atari, then they went on to play Go, which is sort of like chess with orders of magnitude more combinations, much more complexity. And the DeepMind team, now with Google, were able to create an AI to beat the world's best Go players. And that was great. So did we achieve AI? No, not really. So now Elon Musk's team at OpenAI is trying to play Dota 2, which is an environment that's much more complex. It's a strategy game, multiplayer, and they're trying to beat the world's best players in Dota 2. Okay, and it's assumed that if we achieve this, there's progress along with this reinforcement learning AI. So that's the idea behind AI within games. It's basically how smart is our agent. So here's what we're going to do. We're going to talk about the fundamentals. We're going to teach you the fundamentals of reinforcement learning, and then we're going to build out from there. So the central dogma of reinforcement learning, nobody's actually ever said this, but we're just going to call it that, is this. We've got this agent. This is our AI. It's going to be an agent. Dinosaurs are more fun than like the canonical robots. We'll go with the dinosaur. The agent's interacting in this environment. Let's see this grid world. And the way it's interacting is it's taking a series of actions. Okay? So this agent can go up, it can go down, it can go left, or it can go right. It chooses an action. The environment is going to give back an immediate reward, RT, like we talked about earlier. A negative reward for chewing on a shoe, or a positive reward like a treat. It's going to give back a reward, a scalar, and then it's going to end up in the next state. So concretely, imagine you're this dinosaur on the top, and the dinosaur chooses to go down in the first step. It's going to get back some reward for going down, and then it's going to end up in the cell underneath of it, the new state. Okay. And then it's going to keep doing this over and over and over and over and over again. And it seems like in this context, in this environment, what the dinosaur was trying to do is to get to that tree in the bottom right as quickly as possible, because dinosaurs like to eat leaves, or so I'm told. Okay, and what's the goal? Well, like we said, it's trying to get to this tree as quickly as possible. So what it's trying to do is optimize the amount of reward it gets when getting to this tree. So if you think about, like, anybody ever play or seen the game Pac-Man, there's like this monster that goes around and like gobbles up things and it gets points. And the goal of Pac-Man is to get as many points as possible. And that's the fundamental here, is trying to optimize and gobble up or get as much reward as it can. However, we want to motivate this dinosaur to get to the tree as quickly as possible. So the reward we're going to give it is a -1 per time step. So every time this dinosaur chooses an action, like here, it's going to get a -1 reward. And so it's motivated then to get to the tree as fast as possible, because the smallest negative reward is equivalent to the largest reward, and that's what it's trying to optimize. So it's trying to optimize the summation of all the rewards that it gets, and that's called the expected return. Okay, and the expected return, we're going to call it, is also known as value, and that's sort of the language we're going to use going forward. So we're trying to get as much value as possible, or this dinosaur is. And the way it's doing is by finding an optimal policy pi. So what does that mean? So a policy is like, I don't know if anybody here, well, we've all shopped for clothes. My policy when shopping for clothes is to find like the cheapest version of a shirt. Like if I have 5 shirts in front of me and they're all roughly the same, I'm going to buy the cheapest one every single time. That's my policy. When I'm in a state, I have an option I can choose an action, and the action that I'm going to choose is to buy the cheapest shirt. Maybe some of you who are sort of more design-centric, you want the most expensive shirt because you've got style, and clearly I don't. So what you do is your policy is always buy the most expensive shirt. And that's what we mean by optimal policy. So what that means is when this dinosaur is in a state, it has a way of choosing which action it's going to take whenever it's put into a particular state. Okay. And that's what the policy pi is. All right, so it's not pi like 3.14. This is just an odd symbol that was chosen in this realm. There's a technical talk, so I'll just show the math. It's not super important if this math doesn't make sense, but V is going to be our value function when acting on state S under policy pi. And that's equal to the expectation of the return, which again is the summation of rewards when starting in a particular state. There's a gamma in there we'll talk about in a little bit. Okay, does this kind of make sense? Like, we're just trying to get as much reward as possible, and that's the goal of this agent. So how might you solve this? Well, as human, you can look at this grid world and go like, well, I'm just going to go down a bunch of times and then I'm going to make a left. And that's fair. You have that intuition already. But if we sort of make it a little bit more complicated, like what if this maze had many, many more states? Like it wasn't 5 by 5, it was like continuous or like infinite? Much, much, much more complex. Or more, what if there was like more than 4 actions? Like instead of going up, down, left, or right, you could have a continuous action state, or there was 8 actions, like where you could go on angles. Starts to add more complexity. What if you could take an action and sometimes not end up in a different state? So like, or in the state that you normally would expect. So like, you'd expect if you were to go down here, you would go down. But what if like you go down and some percentage of the time you end up like on the other side of the board? Or like, what if like you chose to go left here and actually that's the best action to choose because it takes you right to the tree? But you don't necessarily know that just by looking at this grid. What if the reward signal is delayed? So maybe some action that you choose now has a long-term impact, which we don't necessarily find out about much longer down the road. Or what if you don't have full view of the environment? So like right now we can see everything. Everything's right in front of us. But what if this was like a video game where there's many other screens and states that we haven't necessarily seen yet? Again, it becomes more complicated. And what if, in many cases, when we train these agents, we don't actually know what we're trying to do? Like intuitively, we could say, well, this dinosaur is trying to safely get to the tree as quickly as possible. But what if we don't know that? The agent's just like put into this environment, into this world, and all of a sudden it's like, go figure this thing out. Kind of like our puppy example. Well, there is an algorithm for this. And this is the basis of one of the basic algorithms in reinforcement learning, basis algorithms, if you will, that's been built upon, which again, ultimately resulted in a $500 million acquisition. And it's called Q-learning. So the goal of Q-learning is to figure out, when we're in any single state, what the optimal action that we need to take is. And the idea is if we know we're in a particular state and we know the optimal action to take, then we could just take that action. So for example, if we knew that if we're in the top left here, and we know that the most value we can get is by going down here, then we're just going to go down. Like if there's more value in going down than going left, then going right, then going up, then we're just going to go down. So the idea is to try to figure out a way to come up with a function that'll tell us which action has the most value. We talked about V of S earlier, which is the value of being in state S. Again, that's just how good is it to be in a particular state. Now more importantly, what we're going to build off of is this idea of Q of SA. And this is a value function where we're passing in a state-action pair, a state and an action. And that's going to tell us the value of taking an action in a particular state. Again, concretely, if we're in the top left here, and we say, hey, look, what's the value of being in the state? If we go down, it's going to tell us that. And if we know the values of all the actions in a particular state, then we can just follow that all the way through. And this is sort of the math behind it. I'll just explain it really quickly, but again, don't worry too much about it. The value of being in a particular state when taking an action is equal to the immediate reward we get, plus the value of the next state we land in when we take the optimal action there. And it's multiplied by this gamma, which is a discount factor, which basically tells us how important is future rewards versus current rewards. Okay, all right, so let's kind of walk through this concretely. So again, we're going to set the reward to -1 per time step. Every time this agent takes an action, they get a -1 to try to get them to the tree as quickly as possible. And we're going to pretend like some oracle came to us, some like magic oracle, and created this table. And basically it's a lookup table. And it says, look, when you're in a certain state, like the top left here, we'll call that state 0, what's the value of each action that we take? Up is -9, right is -10, left is -9, and down is -8. Again, these are negatives, so the largest value here is -8. Again, because -8 is greater than -10. So, so we're going to choose to go down. All right, and there's some math that shows it. Okay, then we end up in this next state below. Now here, we've got a bunch of different actions that we can take in this particular state. Again, we're going to choose down because that has the most value. We end up in the next state. And we just sort of repeat this all the way through until we eventually get over to the tree. Now, some oracle, some magician told us these values and made this lookup table for us. So now we can just kind of plan our way through, like we just did. And there's a ton of algorithms for this. Anyone who's done like optimal control, there's dynamic algorithms, dynamic programming, there's A*, there's a bunch of different ways to do it. But what's more important here is figuring out what this table is and figuring out how to build this table. And that's the essence of Q learning. Okay, so how are we going to learn this Q of SA? Here's the math behind it at the top. But really all this math is saying is we're going to take this dinosaur, we're going to run it through this maze a ton of times. And every time we run it through, we are going to record the reward that we get compared to the previous reward, and we're going to update that value function. All this is doing is saying Q of SA gets updated a little bit closer and closer and closer to the actual Q of SA over time. And there's some math that shows that this does converge if you were to run your dinosaur through the maze infinite number of times, going to each state action pair infinite number of times. So again, imagine we're in this grid and we're trying to learn this Q of SA. So we're just taking this dinosaur and running it through and saying, just go through, take actions, maybe randomly, until we can figure out this Q of SA. And every single time we're going to update the Q of SA once we get to the end of the episode. Because that's the goal. Does that kind of make sense? This is kind of like the crux of it. Like if you can understand this part right here, then the rest of it is much downhill, I guess they say, or is it uphill? Whatever. Okay, so the goal is to understand the Q of SA, to learn that Q of SA by running this dinosaur through this maze a bunch of times. Now, how do we choose the actions when we're like randomly, when we're going through this maze trying to learn the Q of SA? Well, one way would be random. You could just like take the dinosaur and say, randomly go in a particular direction, and then over time we'll learn this Q of SA. But it turns out we can do this more efficiently in the algorithm called epsilon greedy. And the idea of epsilon greedy is, okay, imagine you're going to class, and let's say you have the same class every day of the week. 4 days of the week, you take one particular route that you know is the fastest route, or you think is the fastest route to get to class from your dorm, so dorm to class. 1 day of the week, though, you take a different route. You just try something else out, new, okay? And maybe that's actually a faster route, and if it is, then next week you do that route 4 days a week, and on the 5th day, you try a different route. So it is, you're trying to optimize for getting to class as quickly as possible, but at the same time trying out new things, because maybe there's a better approach. And that's the fundamental to this epsilon greedy, this first bullet point, which basically says you choose action A, you go one particular route, majority of time, but some epsilon period of time, this really, really small percentage, you sample from a distribution and maybe you take a different action to get there. This is sort of, the next bullet points are more about the algorithm itself, but what we're doing is you're choosing action A in an epsilon greedy way, and then you're learning against this A prime, which is actually the action that you choose when you end up in a new state. So fundamentally, we're acting on A, but we're learning on A prime, which is the optimal action in the next state we learn on. And this is known as off-policy learning, which just allows us to do a lot of interesting exploration. Because the goal is ultimately to learn this Q of SA, but we want to do it as quickly as possible. It's also known as model-free learning for any engineers in the crowd who've done sort of optimal control. Sometimes when you sort of plan out an algorithm, you know everything about the environment. You know all the transition probabilities. Maybe you know the rewards in this context. And if you were, then you could just sort of plan out your route in advance. But we don't know anything about the environment. We're just learning the value functions along the way. So here's the algorithm in full detail. So we initialize a Q of SA, so that's that table, for example, to whatever. It's like some arbitrary numbers, really small numbers close to 0. Then we loop through. So we start at some random S, so we initialize an S, and we loop through, and we choose an action A. And we take that A, and then we update our Q value, and then we end up in the next state. And we just keep doing this over and over and over and over and over and over and over again. And ultimately, our agent should be able to understand this Q of SA. Okay, so let's just put it into some examples. So we've got all this vernacular here. We've got agent, environment, action, return, reward, state, value, policy, pi, and of course this Q value. So again, to go back to if you're on campus and you're trying to get to class as quickly as possible, you're the agent, let's say. The return or the value is how quickly you get to class. What are the, let's see. The state is where you are on campus, and then your action is like, do I make a left, do I make a right, do I go straight, do I ask for directions, what do I do? And of course, this assumes you don't have an iPhone to tell you exactly how to get there. If you're a golfer, so the environment, of course, is this golf course or this putting green. The state that you're in is where's the ball relative to the hole in that putting green. The action that you choose would be how hard maybe you hit the ball or like the direction that you hit the ball. The reward would be based upon how close you get to the hole, with the optimal reward being, optimal return being if the ball goes in the hole. For the engineers, this has a lot of interest in the robotics community. The agent, of course, would be the robot. I don't know, the action might be choosing where to move a piece around. The reward could be defined by the environment. I don't know, based upon whether or not you stack certain pieces together. But again, okay. And then lastly, we'll go back to Space Invaders, this Atari game that became used in this deep reinforcement learning paper. So in here, the agent, of course, is the spaceship. The reward is the number of points, or the points at each time step. The return, of course, is the aggregate number of points. The action you can take is left or right, or you can fire. And again, we're trying to beat this Atari game. Okay, so we've learned Q-learning, we've learned the fundamental algorithm. So how does this go from 20-minute introduction to Q-learning to $500 million acquisition and glory for all of you when you move out to the valley? It's like, I think it's like, intro is like $300,000 salary or something right now for these researchers. So God bless all of you. All right, so here's a quick intro to deep learning or neural nets. This is very, very simplified, oversimplified, but for illustrative purposes, hopefully this will make sense because it's going to be applicable in a moment. As you've all heard of deep learning and neural nets, like you can't read a tech article without having this vernacular come up. So hopefully it's in many ways maybe overused. But here we go. So let's say we wanted to make a prediction. We wanted to build an AI that can make a prediction on whether or not a student gets accepted at the prestigious College of New Jersey. Well, how would we do this? Well, maybe we just sort of collect a bunch of data. The green ones are the people that got in, the red are the people that didn't. Then we'd collect more data, and then maybe the AI, what it would do is fit a line. It would just fit a curve. And based upon this curve, we could then make a prediction on the next student's information, whether or not they're going to get in. And this is it. Like, this is like the fundamental to what, in the wild, most of AI in the world is doing today. So ideally, if anybody can see this blue dot in the top right, if you can see that, we can all guess whether or not the student got in. Did the student get in or not? Hands in, up, they got in. Hands down, they did not. Okay, perfect. So our AI works, seemingly. We can make it more complicated. We can add another variable or another feature called essay score, arbitrarily. And now it becomes sort of a three-dimensional graph. And we have to fit another curve. And you can imagine instead of like 2 variables or 3 variables, it's got 10 variables, 100 variables, 100,000 variables, tens of millions of variables. This curve that we're fitting becomes nonlinear very, very quickly. It becomes very, very complicated. And that's where neural nets come in. Neural nets are just universal function approximators. That's it. They find ways to create curves. Again, a little bit oversimplified, but so here's how it works. You've got a neural net. This is what it looks like. We're feeding it a picture of a cat. We feed it a bunch of pictures of cats. Over and over time, we feed it more pictures of cats. We feed it some pictures of dogs. Eventually, you feed it a picture of a cat it's never seen before, and the neural net is going to predict that it's a cat. Same thing, over time, you feed it a bunch of pictures of dogs. Eventually, you're going to be able to feed it a picture of a dog it's never seen before, and it's going to be able to tell you that it's not a cat, or it's a dog, or whatever. So, very similar to this, but just at a much, much, much more high-dimensional space. That's all that's happening right now. Okay, why that's important. Well, we've got this deep Q learning paper that came out in 2013, which we've been harping on for a bit here. And in this paper, they tried to create an AI that could play using a single algorithm, Atari at human level or better, over a series of games. There's been a bunch of subsequent papers about this. We're just going to talk about the very first one. And they had a lot of problems because they, at DeepMind, wanted to use this Q-learning algorithm. But the problem with Atari is like the reward signal isn't necessarily immediate in the sense that like you move left to dodge a bullet. Well, that's really important, but you're not necessarily getting a reward for that. Like the AI doesn't necessarily know that. Or you press to shoot one of the aliens, and you don't necessarily immediately get a reward. It takes a couple steps. So we have to figure out how to do that. Data is not independent, so like states are correlated. So you choose an action, you end up in the next state. Those two states correlate to one another. And the data distribution changes over time as the agent learns. So what that means is, like when we were in that grid world of the dinosaur, all the states were right in front of us. We saw everything that we needed to know. With Atari, the better the agent gets, it's going to end up in more states. So the idea is, like, we're going to have states presented to our agent that it's never seen before. So having a lookup table isn't going to necessarily work, because how can we have all the states in there? There's going to be states at all times that will keep coming up. They'll keep being generated that the agent potentially has never seen. So you can't just have a lookup table. Instead, we need some sort of function. So how does that work? All right. We're not going to go through all this math right off the bat. Just really, we'll work our way up to it. All right. So let's pretend like we have some optimum action value Q star of SA. This is like the perfect function approximator. Imagine like this one works. And it's defined as the max policy based upon the expectation of the reward given the state action pair. Okay, so again, it's just like, imagine we've got this perfect Q function, Q star. Well, we can't actually get there necessarily, but we can sort of get pretty close by using a neural net that we saw before, and that's what this Q of SA parameterized by theta is. If we can figure out this theta, which is basically the weights to define that universal function, then potentially we could find a Q of SA function approximator. And the way it would work is we would take a screenshot from the Atari game, we would send it into this neural net, just like we did with the pictures of cats. We'd send this into the neural net. And instead of outputting that it's a cat or it's a dog, this neural net is going to output the value of each possible action that is available to us in this Atari world. So like, if you look on the far right, those are all the possible actions that we can do. This is actually directly from the DeepMind paper. So these are all the actions that the Atari agent could choose from. And it's going to output the value of each one of these actions. And then just like with the dinosaur we chose to go down, we're going to choose the action that has the most long-term value. And that's kind of it. So imagine we set up this Atari environment. We put an agent in there. The agent plays this game a lot of times, over and over and over and over and over again. And eventually, what will happen is when the agent sees the screen, it can know which action to take. And potentially can do it better than any human can. And you can see how this applies to Go. You can see how this applies to Atari. You can see how this applies to Dota 2, or many other things. Like, there's been research on trading. Like, imagine like you could create an agent, you stick it in the cryptocurrency trading world, and it can turn around and make you millions of bucks, or the stock market. It turns out none of that research has materialized. At least in the last paper I read was like a year ago. And the reason is because these environments are very, very, very fragile. In fact, I'll go through this math really quickly, but you'll see that this almost shouldn't even work. Like, it doesn't make sense that it works mathematically, but it turns out it sometimes does. So there's like kind of this like linear, how do I put it? Whenever somebody like learns about AI, and I forget the attribution, I forget who said this, I think it was an MIT professor. He said, you know, when anybody learns about AI, the first thing when they learn about AI, they're like, I don't know what this does. Then they learn about it, and they sort of get the fundamental to it, and they're like, well, I can apply AI to anything. I'm going to solve every problem with AI. Like we said, stock trading, or gaming, or whatever. And then you actually do the implementation, it turns out like the thing falls apart most of the time. So, so it's good to have these ideas, but just understand that we are nowhere near artificial general intelligence. So I'm going to try to explain this, this math on the right. If it doesn't make sense, that's okay. Ideally, like if you got into here, that's great. But for those interested, here's how it works. So when we train like a network on like a cat, basically what we're doing is we're putting an image of a cat through the network. The network's predicting that it's a cat, and then we're telling the network if it's right or wrong. And there's some sort of distance between whether it's right, whether it's right and the actual, or I'm sorry, what it predicts and the actual answer. And over time, by putting enough cats through, enough dogs through, and it learning whether it's right or wrong, it updates the network. okay, through a backpropagation algorithm. So this is called a loss function. The loss function here is this L of theta. And what this is saying is the output of this network, it's going to predict something, but how does it know it's right? Like before with the cat and dog, we could tell the network if it was right or wrong, but we don't have all the states or the action values in existence. So how do we tell if the network is right or it's wrong? Well, we can't. So what the what the DeepMind team did is they used this idea of what's called experience replay. So they basically kept track of every state action pair that they had, and they put it into memory, and then they would predict at each time they were trying to update the network what the value of the state action pair was, and then they would base it on the output of the network from the previous state action pairs that it had gone through. So it's basically kind of like learning against itself. And intuitively it doesn't make sense because we don't have the ground truth. But for some reason, it worked. So let me show you that. So experience replay. So we've got this experience at time step t, which is the state that it's in, the action that it's in, the reward that it's in, and then the state that you end up in when you take that action. Then you've got this experience replay d, which is just all of the experiences that you had. And then what you're going to do is you're going to sample from that experience randomly. In this paper, it was random. And then based upon that, that's how we're going to compute this this y of I and compare it as a loss function. So it's hard to explain without sort of having fundamental of loss functions, but that's kind of the gist of it. Some other implementation points, not too concerned with this. Let's just talk about the algorithm itself. So we initialize the replay memory D to a capacity M, and then similarly as before, we initialized a Q function just to have sort of random weights. And then they just ran this agent through the network over and over and over again, sending in pictures of the environment that were actually pre-processed, so they would take multiple states, combine them together, pre-process them, send it through the network, get out some value for each state action pair, and then they would store that transition in that D that was initialized earlier, and then we would perform this update step based upon that we saw before that loss function, and it worked. It worked pretty well. Here's some of the results compared to other reinforcement learning algorithms. But the biggest point is like versus human. You can see that like in some cases it's better than human in certain games. Other cases it's not as good, but it's still pretty good. And this is like the first attempt at this algorithm using this experience replay with this neural net as is. And what made this all possible is computation, like a lot of computation and a lot of data. One of the challenges with deep reinforcement learning is it requires a lot of data. Like, if we go back to Dota 2, well, just Dota 2, the way that OpenAI trained Dota 2 was something like 180 years of gameplay per day, was it? So like the equivalent of like playing the game for 180 years every single day, or was it every hour? Whatever, over a period of weeks. Like that's how much training it required to get like almost as good as the best professionals who've only been playing this game for 7 years. So just going out and building this algorithm, this is why it fails a lot, because it can explode very easily and it requires just incredible amounts of data. So I've got a slide if anyone wants, just if you want to learn more about reinforcement learning, here's some great articles. I can share this. We'll just do a quick example, the demo. Demos are fun. Okay. All right. So there's a couple different frameworks we're using for doing AI deep reinforcement learning. One is called PyTorch. It comes out of Facebook. It's very Python-y, so it's great. And the code for this is actually directly from their docs. So hopefully, if anyone wants to learn more about it, they can explore that. But let's just look at this. So what are we going to come up with? All right. So I'm on the wrong. Okay, so what's happening here is there is this cart, and it's trying to balance this broomstick, this pole. And in the graph, what you're seeing is each episode. So an episode is defined as like when this pole falls over. And what it's trying to do is learn on its own how to keep this pole up, and you can see the duration in the y-axis over time. And so right now, this cart is learning how to balance this pole using this exact algorithm that we just went through. It's trying out new things. It's getting back some reward from the environment. In this case, the reward is a positive return, or positive reward for each time step, because we want to motivate it to keep this pole as long as possible. And we'll just sort of let this thing run out and see where it goes. But that puts me right at time, so if there's any questions or anything like that, I'd be happy to answer. Or we could just stare at this for a while. Thank you.
Networks that are trained on data that's completely unrelated to what they're trying to do, and then use those to predict what they're trying to, and like it's completely unrelated data that it was trained on. How does that work?
Yeah, so it's an idea called transfer learning. A lot of times it's unrelated, but it's related. So for example, one of the most common use cases, or the canonical use case, or like what's taught is in transfer learning is on ImageNet, which is basically a bunch of categories of pictures. Okay, so the network's already trained on these categories of pictures. And what you can then do, to your point, is then take that network, apply it to another category of picture that's not already in there, and very quickly it should learn, right? Like that's what we're talking about. So like it's already trained, so it's got a ton of categories of pictures. We then can train it on like, I don't know, a tractor that it's never seen before. So the way it works is, on that initial category of pictures, there's elements of each one of those pictures that are universal. So you think about like edges, you think about color schemes, contrast. So what it's doing is it's actually taking all that stuff up to that it's learned, and then we're chopping the head off of this network and applying a new head, so then you can quickly learn sort of the next piece. Does that make sense? Okay, yeah. So in this world, that is huge area of research, because like you can train an AI to play Dota 2, but it's not going to be able to play Go, and that's the goal, is to create an AI that can generalize across different environments. So yeah, there's a lot of research there with variable levels of success. Any other questions?
So we seem to require less training to get to a competent place as humans. I mean, we don't need a billion iterations to figure something out. So does that suggest that whatever mechanism our brains are using is categorically different?
Yes and no. Okay. First off, like people use neural net, and with the idea of like as an analogy to the way the brain works, and it's like an insult to neuroscience. But okay, so one of the things that humans have is we know that we have from like day one as a child, like we have sort of an intuition and an instinct around whatever. So like there's videos of like dads sticking out their tongues and the baby able to reproduce that immediately. So there's something about us being human that allows us to have prior knowledge in an environment. And that prior knowledge, when applied to a video game, is really, really helpful. We pick up an Atari game when we know that aliens are bad and there's spaceships, and we can, we don't have to relearn all that stuff. Where an AI doesn't have any prior knowledge. It doesn't know what an alien ship is. It doesn't know what aliens are and shooting is. So that's one of the reasons why this takes more time. But it's also really interesting because, like, for example, in the Go, we're always thinking we want to imitate humans. But in Go, I think it was move 37 or whatever, the AI itself actually learned to do things that humans had never thought of before. And so now, as humans, we can actually learn from the machine, because the machine can explore things that as humans, we are predisposed to doing things certain ways that we may have not even considered even trying, or necessarily able to understand or comprehend. So I don't know if that helps. And that's what's so exciting about reinforcement learning, is because the AI can actually learn things beyond the scope of what humans are capable of doing in theory, given enough data. but there absolutely is a huge area of research as well, is like sort of giving this AI prior knowledge so that it can learn quicker to this example of transfer learning. Yeah. This orange line, by the way, is I think that's the average of all the previous durations in the past 100. So that's why that's what that's doing. And any other questions?
Yeah. Traditionally, the most difficult part of the reinforcement learning is the design of the real function. And will the deep reinforcement learning has the same problem, or is there any improvement in that sense?
Yeah. So the question has to do around reward shaping. So like, we could set up an environment where we can set up the reward to help motivate this this agent to do things more quickly. The problem is, as soon as we start sort of massaging that reward, the agent can learn to do something that that we might not necessarily have thought of. So like the classic example is like a robot that you want to clean up your dishes, and it gets reward for cleaning up your dishes. Well, eventually, this is a thought experiment, does the robot learn to like start breaking dishes because it gets a reward for cleaning them up? So defining that reward is a challenge, and ideally what we want to do is keep the rewards as sparse as possible so that that gives the agent as much time to explore as possible, as opposed to us sort of dictating what that agent should do, because then it can learn sort of beyond the scope of what we necessarily had thought of. But no, it's still a huge challenge. Reward shaping.
So there was a particular slide, I don't remember which one it was, but you said something where the artificial intelligence wouldn't be perfect. I was just wondering if you could clarify that.
Yes. Let's see if I can find a slide. By the way, pro tip: if you're ever giving a presentation, someone asks a question you don't know the answer to, just say, "Oh, we're going to get to that in the later slide," and then just. All right. What were we talking about? The question was. Wait, no, that's really exciting. We want to keep this up. True AI. Oh, yeah. It's what we're talking about. Oh, we're talking about the gameplay, and yeah. So AI in itself is like sort of an ambiguous term that's probably overused. The definition of it is vague at best, like depending on like which world you're in. Like the business community, it's one thing, and the research community is another. What I was defining it as in that context is the idea of an AI that could generalize across different tasks. So what happens is in these games, the AI gets overfit to playing that game. It can play that game really, really, really well, but it can't play the next game really well. It has to be retrained and retaught to do that. So when I was saying true AI, what I meant by that was just an AI that you could stick it in anything and it would learn really, really quickly. That's what I meant. Any other questions? Well, we're at episode 140. It's going to do pretty well. But I mean, it goes to show, like we're already like 5 minutes into this, and it's. I mean, my laptop's not anything great, but like we haven't gotten very far. You know, it's just how hard it is. Yes.
So, can you talk a little bit about your own experience with this?
Yeah, absolutely. My experience with this, like anything, is really just me spending a lot of time just hacking on it for fun and not always for profit. Just building models, toy models, whether it's playing with whatever like the latest, greatest thing is, or doing some simulation around like one of the students here, Keith, he's doing some drone experiments. So I actually had implemented that prior just for fun. And that's most of my motivation, is just to hack, keep learning. Yes?
So following on that question, so are you planning to start up the company that's using this?
Well, you gotta ask Brad that. I don't know. I mean, the problem is in production, it's really, really, really hard to do. There's a paper. There's a DeepMind paper that I'm gonna mess this up. That at the bottom of the paper, there's an asterisk in one of the comments. And at the bottom of the paper, it says this Google DeepMind says we couldn't conclusively draw whatever, or we didn't know with certainty the conclusion. Basically, they skipped out on the answer. And the reason was because they didn't have enough computational power to make that conclusion. And this is Google. Like Google. So like that just goes to show if they have challenges because of computational resources, then like, you know. And the problem, like I said, is these networks blow up all the time. Like one of the biggest problems in the deep reinforcement learning community is people release a paper and then somebody will go to like try to implement it and they can't do it. And it's not because they don't know how to write code, it's not because they don't understand the algorithm, it's because the person who wrote the original paper got lucky. Like they just got lucky. You know, their cart stood up. And so that's one of the challenges and one of the big things in the deep RL community is writing papers, but also the code to support it so that people can reproduce their results. Because a lot of it, for a long time, is just kind of bogus. So as far as doing a startup around it, it'd be a lot of fun. I mean, you get a lot of press. Everybody would be talking about it. But I don't have an answer today.
At FrontRush, did you use any of that stuff towards the end to do the recommender, to recommend certain, like?
We didn't use any reinforcement learning algorithms. We did use a lot of like machine learning algorithms, like prediction. But like in terms of application, like robotics, like are there engineers in here? Not just computer science. Anybody taking like any engineering microcontroller courses or anything like that? No. Okay. Well, so when you like your thermostat, for example, you change the thermostat to like 80 degrees. There's a controller in there that determines how long your heat should run to get you so your environment is set to 80 degrees. Well, that uses what's called a PID. Well, you can imagine using reinforcement learning to replace that controller because that controller itself is very human hand-tuned. Like humans are going in and like tweaking variables, where a reinforcement learning algorithm, you could just run it through and get sort of the optimal parameters in a much sort of algorithmic fashion. Again, find solutions that we may have not come up with. So there's a lot of research. So I'll give you a quick example. Peter Beal, who's like the Superman of this space, him and his team, researchers, Chelsea Finman on the team. Oh, she's a rock star. Anyway, they're from Berkeley. They're a professor from Berkeley. He's a professor at Berkeley, and he just raised like $7 million over the summer to start a robot company that uses deep reinforcement learning and aspects of it. And like, there's no output. Like, there wasn't like a clear product that they were selling. But people are so excited about the potential of using this in the robotics world that like they just wrote him a really big check and said like, go have at it. And I can guarantee that there's millions and millions of dollars to back that one up once he burns through that because they didn't figure out anything necessarily to produce. Like the bleeding edge. The bleeding edge, so there's a conference, it's an AI conference called NIPS, which is so hot, it just sold out in 12 minutes the other day. They had an example, Peter Beal and his team had an example of a robot that basically could learn to, what did it do? It could watch a human pick up a tray and move something to another location. And then just by watching it once, it could then do that. And like the thing worked like 60% of the time. And this is like the bleeding edge, like the best in the world working on this stuff. And their robot like only worked like 60% of the time. So the potential is enormous, but the existing promise is overhyped for today's standards.
Is there a huge difference between where we are in terms of research with kind of knowing the goal and kind of optimizing to get there, and inferring the goal on your own? In other words, are they worlds apart?
Where we want to be and what?
Yeah.
We're far out from there.
On the ladder.
Assuming that the goal is artificial general intelligence,
Yeah.
like the AI overlords.
In other words, machines observing and figuring out what it needs to do in that space.
Yeah. Now there are things that have been solved, like vision. Like computers can see now.
Right.
I mean, they can see really well, and that in itself has a lot of application
Yeah, so what I have in mind is, for example, a game of Go. Instead, are all of these presupposing an outcome that's fed into the machine? This, in other words, is what victory looks like? Or is it always about inferring what success is? You see the distinction in that? In other words, what are we optimizing for? What value?
Yeah, I mean, let's see. So what we're trying to do is we're trying to, well, I mean, I guess it's just a sort of an iterative approach. So we solve Go, then we try the next thing that's a little bit more complicated, and try the next thing that's a little more complicated. Right. And we drive down computation costs, and we improve algorithms, and then the output that we're solving for is we can do things that humans don't need to do any longer. We can build things that humans aren't capable of building. We can take away millions of jobs so that we don't have to work anymore. That maybe exactly.
So things like Tesla's self-driving automation stuff, is that machine learning or is it?
Yeah, it is. But think about like reinforcement learning in a self-driving car scenario. Like, hey, car, go out there and just like try it. You know, like they're going to get in accidents and it's not going to be fun and a lot of lawsuits. So you, in a simulated environment, you could absolutely use reinforcement learning. In fact, it's been done. There's a ton of tutorials on it. But they're using a combination of vision. They're using what's called behavioral cloning, which is the idea that you're recording someone driving a car, and you're seeing what the car sees, and the person makes a left at a certain state, you know, and then they make a right in a certain state, and then for that we're learning. So we're learning like what the person's doing based upon what they're seeing. And there's millions and millions and millions of miles of Tesla vehicles going around, and that's one of the ways that it's learning. But there's a bunch of sort of combinations to that. But yeah.
Do you think that the same type of AI would apply to like businesses in the future?
Yes. And sorry, yes, I cut you off.
No, it's okay.
Just in general?
Yeah, just in general, like businesses, like let's say banks or any type of department stores. And my question was like, what would it apply to those like costs like in the future?
Yeah, like logistics, absolutely. Inventory, like how much inventory should you keep at a certain period of time? How do you route cars? Like if there's a CS students here, like you've done the traveling salesman problem, like that can be solved using reinforcement learning. You know, if you're a salesman, you're going all around the country, like what's the optimal way to get there in the shortest period of time? This absolutely can solve for that. So yes, it totally should have application. It's just as it gets more sophisticated, it gets more complex and harder to do without enough data.
I have another question. Like if you were, like in a brief estimate, like how many years do you think we will get to that point that reinforcement learning could be applied to?
Sorry. How many years? I'm not going on record saying that. The question is how long before reinforcement learning is sort of applicable, and like we can. Yeah, I'm not going to stipulate. Let's say 5. No, I don't know. It depends who you ask. It's just really the trajectory is going much faster than anybody ever expected, for sure. It's just that when you hear people talk about like AI taking over the world tomorrow or in 2022, like they're full. They have no idea. They're just guessing.
Okay, last question.
Maybe somewhat unrelated or maybe related. I don't know. You tell me. What is your role here at PCNJ?
Oh, as an entrepreneur in residence. So,
what do you do?
so it's an apps. So to help in any way facilitate sort of innovation and entrepreneurship on campus, whether that's through professors who have an idea to grow IP, or students who have a business idea or an agenda, or just have questions, or whether it's sitting in on Professor Michael's class and helping to provide our experience, to explain how we did things in the past and how that might apply to somebody's business initiative. So really anything around innovation and entrepreneurship, we probably want to somewhat be involved in.
So you would come and visit CS classes too?
Anytime. Yep. And Professor Hollywood, I sat in her class last week, and that was a lot of fun. A lot of really, really brilliant students in that class. And so, yeah, we're happy to be involved in it. Brad was actually just at the Entrepreneurship Club meeting last night, and just had amazing things to say. And so got some takes on that could help. So if you have any ideas, I'd be happy to jump in. Please do. Yeah.
Okay, thank you very much. Let's thank our speaker again.